All right, come back to me. 3, 2, 1. All right, so as a quick reminder of those decompositions, we have 4 types of decompositions, right? Binary always break down to what? Just the 2 elements that they're comprised of. Metal chlorates always break down to metal chlorides and the friendly gas oxygen, right? We're not going to make chlorine gas because that would kill us all. Metal carbonates break down to
carbon dioxide.
Metal oxides and carbon dioxide, right? Carbonate and carbon dioxide is the gas. And metal hydroxides break down to
water, H2O.
And metal oxides and water, right? And a lot of these are under heat, so that's where we're making a lot of gases, because gases tend to come from one decompositions and if they're heated. So that's probably like gaseous water, like water vapor, if anything. Okay? So if you need to rearrange your bodies, like you 3 guys, come find a seat over here. We got some empty spaces. Come on over. And we are going to talk a little bit more about single, double, and combustion today. So we're going to add on to our foldable. So how does that work? Okay? Question? No question. Okay. So I want to go back and do like 2 from here, because you guys started them and you're supposed to try to do them from memory. Try. So remember, your first step is to always identify the type of reaction. So if I have aluminum reacting with sulfur, I have an element with an element, what's the only thing they can really do? Combine, right? So that's what kind of reaction? Synthesis. So when I write aluminum, I legitimately just write aluminum, just aluminum. Guys, there's empty seats up here too. The live station's not your only option. I'm just letting you know, okay? Sulfur, how do I write sulfur? Just S. There's nothing is diatomic at this point. And which should I form? What's the name of the compound I should form? Aluminum sulfide, right? And then what's the formula for that? Al. Say again? 2S3. Because remember, you're crisscrossing charges every single time you make an ionic compound. And that would mean I need a 3 here and a 2 here to balance them out. Moving on. If copper 2 reacts with phosphorus, which is the third one right here, copper 2 reacts with phosphorus. I have copper 2 and I have phosphorus. So I have 2 elements. What's the only thing they can do? Combine again. So yet again, we have a binary synthesis. So how do I write this? Cu. And I do not want to write a 2. I don't want to write a 2 plus. I don't want to put a diatomic 2. Why do I have to tell you this here? So you know the charge, because later on we're going to have to do what with charges? Crisscross them. So I need to tell you that up front, but do not include it up front, because that's not how we indicate the element. It's just copper. And phosphorus is just phosphorus. Combined to make what? Cu3. P2, good, because copper had a 2 plus as it was indicated over here. Phosphorus is in group 5, or 5. So it's got a 3 negative charge, crisscross those, and we put a 2 and a 3. So that was the only really weird one I wanted to expose to you now, because you'll find that you feel tempted to put the 2, but don't put it until you crisscross charges. Okay, and then lastly, let's do one of these on the bottom. Let's do aluminum carbonate decomposes. Okay, so obviously it's a decomposition reaction. What was the dead giveaway? Single reactant, right? Single reactant. I know it says decompose, but you should see the single reactant and go, okay, that's definitely decomp. What's aluminum carbonate? Spell it out for me. Al2.
CO3. Oh,
parentheses. 3. Good, because aluminum has a 3 plus charge. Carbonate has a 2 minus charge crisscross. So decomposes. Put a little triangle on top to indicate heat is usually applicable here. And what do all carbonates always make?
Carbon dioxide.
Carbon dioxide. Like I said yesterday, it doesn't matter if I put that first or second. It's just 2 products forming. And then we make metal. So yeah, so it's a metal oxide. So who is it here?
Aluminum oxide.
Aluminum oxide, which would be what? Al2O3. Good. It looks like you guys are crisscrossing charges, at least people who are responding. Do not forget to crisscross charges. That's really the biggest mistake people make when we're predicting products. You're just like happy to get through with it and forget to crisscross charges. And then, is this balanced?
No.
What do I need?
Well,
I got 2 aluminums, I'm happy.
You need 4 more oxygens.
Well, I've got how many oxygens here? 9, so that's 3 times 3. The parentheses and the subscript are right next to each other. That is going to be multiplied, so that's 9. I have 5 here. What else is wrong?
There's already.
So how many carbons?
On the left side.
So there's 3 here and 1 here. So I'm going to put a 3 out front here, and that should satisfy my oxygens as well. So that's 3 times 2, 6 oxygens, and plus the 3 is 9. All right, give me out of predicting for synthesis? 1 out of 10, where are you at? Predicting for synthesis, that's memorized at this point, okay? You're trying to get it in your head. You do not have to be a 10 at this point. Literally, you just learned it yesterday. You practiced it for less than 24 hours. All right, decompositions. Decompositions, 1 out of 10. I see numbers go down. Decompositions are a little harder because you have 4 of them to remember. And then balancing. Balancing, 1 out of 10. This is my survey. You must participate. Okay, most of us are right. That's great. Okay. So we're going to do, let me show this video first. So we're doing a lab next week, and in our lab, we're going to make gases. Well, if you look at a gas, how could you tell what it is? You can't, right? So we have to have test for gases, or test to indicate what type of gas is forming. So we're going to watch a quick video. It's like 2 minutes. I want you to write down the 3 gases he tests, how he tests for them, and what indicates what type of gas it is. So what are you writing down? The gases he tests, how he's testing them, what indicates what it is. Okay, try your best, okay? All right, testing for oxygen. Ooh, what happened? Let me get rid of this ad down here. I'm gonna start this over, sorry. Alright, so this is our first test. He's lighting the splint on fire. That's not the test yet. So testing for oxygen. He's got oxygen in this tube. And he blew the splint out, but what happened? It reignited. He blows it out. He puts it back in, it reignites. So oxygen will reignite a burning splint. So hydrogen gas is what he's testing for next. He's just putting a little something in there, magnesium and hydrochloric acid. He's trying to make some hydrogen gas. So he puts a burning splint, and you put it in. That's called the hydrogen pop, hydrogen fart. So lime water is the key on this one. It's clear, you can't see anything. Lime water is what he's put in the test tube. And now he's going to add some agents that are going to make carbon dioxide. So hydrochloric acid and carbonate make carbon dioxide, like we mentioned already. Carbonates tend to make carbon dioxide. He's setting up a fancier experiment than we will. So he's bubbling carbon dioxide from this tube through the air, through this tube into this tube, which this tube had what in it? Lime water, and it was clear. And now the lime water is going to be like a dingy kind of off-white color, milky color, as they call it. So carbon dioxide turns lime water milky. So that's like a liquid carbon dioxide test. This is a gaseous carbon dioxide test. What's happening? Carbon dioxide is in that, and it's putting out the flame, right? All right, that was fast. I should have slowed that down for you guys. But let's write them on the board so we are clear. Will you get the lights for me, Karen? All right, so for the 3 splints, 3 flaming, yep, that's good. Splint test. He did oxygen test, he did hydrogen test, and he did a CO2 test. What happened on each of these? Oxygen did what? Reignite the flame, and hydrogen does what? Made it either a pop or a bark. You'll hear ours. It'll go like, arr! like that, like a little dog. Okay, and then CO2 should do what to the flame?
Put it out.
Okay, so suffocate or put out. Okay. And then lastly, he did the lime water test, and it went from clear to milky or cloudy. Go sit in the back and put earphones in. Thank you. Don't disrupt class. And that was testing for what? What was the lime water testing? What gas was it?
CO2.
CO2 again. So CO2 can be tested in 2 different ways. There was an exam question like this, maybe just a couple years ago, and nobody got the lime water question right. Nobody. So it was kind of a shame, but it's such an easy way to remember. If you remember, like, milky, well, it was calcium carbonate, but anyway, we'll get back to that. All right, so this is information you'll be putting in your foldable. Remember, you're looking for a diagram or an illustration. Looking for the definition, which is a lot of times kind of what's up here on the front, the top of my slide, and then the general form, which is going to be just letters to indicate what's happening. If you want markers and such, I do have them here if you need them. I'm going to scroll down just a little bit for you. All right, let me scroll back up in just a second. I'll let you finish writing your generals down. And Aiden's going to pass out the activity series for you. So make sure you get an activity series. They are my class sets, so please don't pilfer them from my room. You feel free to take a picture, though, of both sides if that's something you wish. That is something that you'll utilize during like problem sets and homework to indicate if a reaction is going to occur or not. So feel free to take a picture if that's what you need to do. All right, so single replacement. This one makes a whole lot of sense. It's very logical. So you have a single reactant. So here's my general form. You have a single and you have a compound. So the single element wants to be in a compound. Everybody wants to bond. Everybody wants to make an ionic or covalent structure. Because it's energy lowering, it's valuable. So A wants to be in the bond. So who does it replace here? So it kicks B out, right? So A takes the place of B, so then it's bonded with C. And in this example, A takes the place of who? C. So they must be different scenarios, like one's a metal, one's a non-metal. That's kind of like the idea behind this, and that's what this up here was saying. Cations can replace cations if they can, if they are active enough. We're going to talk about why the activity series matters. And then anions can replace anions if they're active enough, if the activity series says so. So basically, not like if you have a partner, let's say Cole and Bailey are partners, and they're just a really solid partner set. They both work hard, And Hannah's like, Cole, can I be your partner? Can I be your partner? Can I be your partner? And Cole's like, sure. You're going to kick Bailey out of the partner set, and Hannah and Cole are going to be partners, right? Well, sometimes that's not going to happen. Sometimes he's like, no, like Hannah doesn't work hard enough. I really need a solid partner. He's like, nope, we can't do that. Hannah's not going to be my partner. So what's going to constitute for chemistry? What's going to say yay or nay if it's going to react or if it's going to replace or not? Because if Cole's like, no, Bailey's a solid partner, I'm not going to lose him, Hannah's not good enough, then he's not going to do it. But there's got to be some characteristic that he's looking for. Well, in chemistry, we're looking for activity, okay? So the activity series, turn over, it's on the back of the laminated little card set. So the ones at the top of activity series are most reactive, okay? So the ones at the top of the activity series are most reactive. So if they're coming into the reaction, if they're they're the singles, they're like, somebody's going to react with me, and I'm going to get in that ionic compound. Like, they are going to react. It's totally going to happen. But if you're at the bottom of the activity series, you're not very reactive. So you're going to go, can I partner with you? And you're just not reactive enough, so you're just not going to force the reaction to occur. So this would be unreactive, or relatively unreactive. So we have to have the activity series to predict these. If not, you're just using this off the top of your head, which isn't very, very reliable. So do you know on your little general formats, the cation and ionic nature of these? So would A be a metal or a non-metal in this first scenario? Why? Because B has to be a what here? A metal or a cation, right? So these are ionic species. B is a positive cation. C is an anion. Same thing down here. B is a cation. C is an anion. Because anytime we write ionics, we always write cation and then anion. That's always the order. So if A is switching out with B, A must be a metal, which has the potential to form a cation. So metals have the potential to form a cation. And so that's why B gets kicked out. So B's just not active enough. It's not a good enough partner. And then here, this is a metal. This is a non-metal because A is switching with C, which is the anion, because anions are going to be non-metals. So that's kind of your guide there. So look on the very top of the activity series. Isn't there a little non-metal activity series? You see the halogens? The halogens are the only non-metals we really consider. But look at this order and look at the periodic table. What do you notice? Same order. They're all in the same group. So who's the most active or most reactive of the halogens? Fluorine. So if fluorine is present as a single guy, it's going to take the place. It's going to totally switch out partner sets. And if iodine's present, maybe not. Kind of depends because it's the weakest, it's the least active of them all. And then lithium, right, is at the top of the activity series for the metals, and gold is at the bottom. So lithium is going to react and the other ones are not, or not be as reactive. All right, so let's look at how this applies in a situation. So write down these examples for me, okay? Just write down the reactants first. If you don't put it in your foldable, it's fine. You need a couple of examples to work with so that you can see how it's going to play out. If you squeeze it in your foldable, that's also great. Do me a favor on this one and write water not as H2O, but as what? HOH, just to clarify how we can look at this a little bit easier. What's hydrochloric acid, Maverick? Hydrochloric acid. Somebody at your table, help me out here. C, that's carbon. Cl, there you go. Hydrochloric acid. And then, is this how bromine goes?
Yes.
2. Why am I putting a 2? It's diatomic by itself. It needs to be diatomic. And what's potassium iodide? K. Ki, because everything's 1 plus 1 minus. All right, so we have our 3 reactants, or 3 sets of reactants. All right, so look on your activity series. Where is the single calcium? Where is that?
Sort of joined.
It's towards the top. So you're saying calcium's pretty reactive. But what we need to know is it reactive enough to break up water? So if you look on the little lines, there's long arrows. Do you guys see calcium?
Yeah.
And it says only these top 5 or 6 can replace hydrogen from cold water. These can replace hydrogen from steam. These can replace hydrogen from acids. Yada, yada, yada. These can replace oxygen, blah, blah, from oxides. We really never use that one. Or no, we actually always use that one. We just don't ever look at it. So we see that calcium is in the range that it can replace hydrogen from cold water and replace hydrogen from steam. So does it really matter what kind of water we have here? It's active enough to do some damage to water. So who is it going to replace? Who is it going to switch with? Yeah, because this one has the ability to form a positive charge. Calcium is a metal. Hydrogen definitely is a positive charge, whereas hydroxide is a negative charge. So these guys just switch. And when you switch, who does calcium bond with? To make what? What's the formula for calcium hydroxide? Nope. CaOH. 2 like that?
Oh, no.
With parentheses, right? So this is calcium with a 2+ charge, hydroxide with a -1, crisscross charges all the way. All right, so calcium's like, all right, I have a bond. I've bonded with hydroxide, and poor old hydrogen gets booted out in the cold like that.
No. It's a diatomic.
Because it's diatomic, it's H2, so it's hydrogen gas. How can I test for that in the lab? Flaming splint test, and what would happen? There we go. Arf! It would bark. Right. All right, is that balanced? No, it's not balanced. What do I need? What do I need? 2 infernal water. Good. And that works. Okay. Now, zinc plus hydrochloric acid. I want you guys to do this next 2. Actually, you guys do this. You decide, 1, do they react? And how do they react? We're going to compare it to that. So where's that in the arrows? All right, so let's talk about these together then. So we're looking at zinc, and we're looking to see that zinc wants to get with who in this combination? It wants to get with chlorine, right? But it needs to replace who? Hydrogen. So we're looking to see, are these going to switch? That is our big question. So we look at zinc on the activity series. We look at the line regarding acids. Is zinc able to replace hydrogen from acids? Yes, it's in that arrow range. So yes, this will happen. Yay, this will happen. And what will zinc form?
Cl2.
Why Cl2? Because zinc has a 2+ charge always, chlorine has a -1. Not because chlorine is diatomic. That would be it by a singleton by itself. Okay, so there's zinc chloride, and then poor old hydrogen gets booted to the cold again as hydrogen gas. And what do I need to balance? Boom, done. Okay, so far both of these have reacted. Bromine and potassium iodide. Who is bromine trying to get with?
No. Potassium.
Why potassium? Right, because bromine is a nonmetal. So if I have bromine wants to get with not iodine because those are 2 nonmetals, and we're not talking about covalent terminal ionics because it's cation and anion interactions. So bromine wants to switch with iodine to make this happen. So can bromine switch with iodine? How do you know? Done.
Because it's on that.
Right, so bromine is 3rd in line for reactivity. Bromine is higher than iodine, so it's like, get out of here, iodine, you're getting booted to the cold, as I2. And how do I write this combination?
KBR,
Why KVR?
because they have one this order.
Right, well, tell me why it's this order. Why is it not BRK?
Oh, because it's cation.
Right, because cation goes first, that's a 1+. Bromine is an anion. When it forms a charge, it's a -1. So it's got to go, that's a negative. There you go. It's got to go second. So that's KVR, 1 and 1. And then I need a 2 here to satisfy bromine, and a 2 here to satisfy potassium iodide. Yes? Okay, so far we did 2 cations and then 1 anion replacement. We're going to do 1 more. Can I go past this? Almost. All right, so write this down for me. Copper 2, just to note the charge, okay, copper 2 plus sodium carbonate. So copper 2 plus sodium carbonate, and decide. It's okay. You can be involved. We'll just be a little embarrassed with some good stuff. So we have some lovely volunteers just jumping out of their seats. So can you guys make sodium carbonate? I love you. You're not sodium. All right. So sodium carbonate, right? Lovely sodium carbonate wave, and that formula would be what? Na2CO3, because that's their charge is pushed across. And then we have poor old copper over here. I know she's a 2+, but she's covering up her charge for me. All right, so will this reaction occur? Why no?
Because sodium is more reactive.
Because who's more reactive? So we're comparing sodium and copper, and we're looking at on the list. And sodium's already in the bond, right? So sodium's the reactive one because it's high on the list. Copper is really low, or medium really low on the list. So sodium's like, I'm more reactive. I'm sticking with carbonate, right? So poor old copper, you just sit and chill. You're never going to have a life partner, ever. Cool. Sorry. Okay, so what if I have this reaction? I have whatever here. Name this compound. You guys know what it is.
Copper carbonate.
Copper what? Copper 2 carbonate. And then look at sodium. She's flaunting it. She's like, all right, we don't want to react with. So is this one going to happen? It's going to react. Why?
Because copper is far down the list.
Because sodium is what? More reactive because it's where on the list? Higher on the list. So react. Peace out, Bailey. Yep, you just got replaced, sir. Woo. Okay, so then we would see this like solid copper-colored precipitate. He precipitates. And he precipitates. You don't have to. Okay, so and then sodium carbonate would form. Woo! Drop those on my desk. Thank you. All right, so no, thank you. You were lovely performers. A++. Okay, so put if no reaction, put in R. So if you have a situation where the reaction would not occur because the activity series does not allow for it to occur, put in R, and that will help me know that you recognize it as a no reaction. All right, so single replacements literally does a single replacement. Piece of cake. Just got to look at the activity series to get those right. Double replacement. This is your next piece. Double replacements are actually easier than single replacements. You can't get it wrong. If you switch them both. Yeah, put this in here. So you're noticing so far a lot of ionic stuff's coming into play. So charges matter. Push-crossing charges matter. So if you think single replacement, you have to remember activity series is very important and will apply here. Now in double replacement, you're going to be using these things called the solubility rules, and I'll tell you why momentarily, but it's in the back of the activity series. So flip that little laminated sheet over. So here's the story on this one, okay? So a little inspiration for you, for your memory. So who knows I have a twin sister? Does you have a twin sister? I have an identical twin sister. Yeah, for real? Here.
Were you serious? You really
Like, for real. Identical twin sister.
Well, she knew that, right?
Okay, so proof.
You know you didn't crop it.
I have birth certificates. Okay. Anyway, so now you know I have a twin sister. I'm 6 months older. Okay, so anyway, I'm the older one. But so she had a boyfriend in high school, and I have a boyfriend now, my husband. Yeah, we were sophomore sweethearts. I don't know why you're clapping. That's weird. But so she had a kind of a cruddy boyfriend. So we said, okay, let's see if we switch one time, if they'll figure it out.
Oh no.
Okay, just will they figure it out? Because that means that they truly know us, and we're good to go. So we switched. So this is in-law and boyfriend 1, and this is in-law sister and boyfriend 2, and we switched, and it didn't go so well for her because her boyfriend did not notice. He didn't know her well enough to notice. Mine was like, I know you're Sammy. Like I know it. She was like, shh, we're trying to figure this out. So we did a double replacement. Didn't work out well. So hers they ended up breaking up. So that happened, but we were still together. It worked out. Okay, we got 2 dogs. Happy home, yeah, stuff like that. All right, so basically double replacement, both parties switch places. That's it. You can't get it wrong. The only way you can get it wrong is if you put the wrong thing with the wrong thing. So remember, in chemistry, cations bond with anions all the time, okay? So A is a cation, B is an anion, X is a cation, Y is an anion. A has to get with who? Y to make a cation anion, and Y has to get with B. Okay, so that's the only weird thing, is just making sure you're ordering them correctly. So let's do an example with this one. I'll show you those in just a second, okay? Hold on, let me go to examples and we'll go back. So silver nitrate and sodium chloride, go. Write this example down. You need an example in your global, so why not, right? I also think I printed these specific ones for you, if I remember right. If you can go ahead and attempt this thing on the double replacement, I'll be on you right now. All right, so let's make sure that first one is right. Silver nitrate, Bryce's table. AgNO3. I like that we're putting parentheses because this will help you see like piece 1 and piece 2. It'll help you see cation and anion better, so you don't break up the happy family nitrate. Chris's table, sodium chloride. Chris's table, sodium chloride. NaCl. All right, so who's the cation in partnership 1, everybody? Silver. And who's the anion in partnership 2? Who? Chlorine or fluoride, right? So they have to get together to make what? AgCl, because this is a 1 plus and a 1 minus, no subscripts needed. All right, then in this one, nitrate's a negative and sodium's a positive. How do they get together?
Sodium nitrate.
Good. No one said nitrate sodium. If it just sounds ugly, it's wrong. Right? If you put Na or put NO3, Na, just it sounds bad coming out of your mouth. It's wrong. Okay. Sodium nitrate, and I'm gonna keep that parentheses there so we can see it stay intact. So with our double replacements, don't you be a homewrecker and break up that little happy family polyatomic ion. Keep the polys together. Like nitrate didn't get broken up; it just kind of transferred to a new partnership. All right. So we have a balanced equation, right? Yeah. Okay. So it's balanced. So let's go back to the solubility rules, which is the piece I just skipped. Because basically, we can put this on paper and go like, yeah, this reaction's going to happen. We just switch partners and we're good. But we actually don't know if it's going to look to be actually occurring in the lab until we do it in the lab, or we have the solubility rules to help us see, is this going to happen? Because what we're looking for is there a precipitate happening? And if there is a precipitate happening, we have a chemical reaction because we are seeing a chemical change. So we want to look at this one and this one and go, okay, are one of you guys going to precipitate? And here's how we know. On your solubility rule list, this is the one you have, yes? Sometimes they look a little different, but I like this one because it gives you the ions out loud with no secrets on what they are. So the soluble, and you might want to write down these terms at least, soluble and insoluble sets of compounds are as follows. What do you think soluble means? Do you think it means it dissolves or precipitates? Dissolves. It just sounds like it's soluble, like it's gonna mix together. So this means it dissolves, meaning it will be aqueous. So we would put AQ next to anything that we classify as soluble. So what's going next to solubles? AQ. And if it's insoluble, what do you think it means? It doesn't dissolve, therefore it precipitates. So we would put PPT or S or downward facing arrow to indicate something is insoluble. All right, so what we're dealing with on this example is silver chloride and sodium nitrate, right? All right, so where are the nitrates? Which classification are they? Okay, this means that they're all soluble. There are no exceptions to this rule, 100% aqueous. So on the example we have here, we're going to put AQ next to nitrate, next to sodium nitrate. And then on the other one, when you look for chlorides, where are the chlorides? Okay, so we're like, hey, that's aqueous, right? And then we look and we say, except compounds of blah, blah, blah. And we see silver as an example there, or as an exception. So that means that this one, silver chloride, will precipitate because it's an exception to the dissolve rule. It's an exception to the aqueous rule, meaning it must precipitate. So then we put PPT here to indicate that silver chloride is going to follow through with precipitation, and it's going to be a reaction. Because if we see a precipitate, it definitely reacts. That was a lot of instruction. Try out 2 and 3 here, and then we'll talk some more to make sure you got it. So if you find that there's these solubility rules and they don't list what you're looking for, that's because there's like a bajillion solubility rules, and I think I provide you with like 12. So I have to give you some help on some of these. So if you can't get it, just hold off. the second or the third one keep them already. Because on the second one. All right, let's talk solubility on these first two, or this first example. Which one was not provided for you? Chlorides, right? So you might notice that chlorides, bromides, and iodides all act very similarly. Now, I'm going to tell you fluorine acts similarly. It's got a couple of nuanced details, but it's going to act very similar to these, okay? But I give you these because the AP exam, the honors chemistry exam provides you these. There are tons of other solubility rules that are not here because why give you more than you need if this is all that they're asking you to really know how to use. So if you have fluorides, what was the example? Lead, right? Lead 2 fluoride. Will lead 2 fluoride be soluble or insoluble? So, well, most of the chlorides, bromides, iodides, and fluorides are soluble, right? But then you look at the exceptions, and what are all these exceptions including? Lead. So will lead 2 fluoride be soluble or insoluble? Insoluble, because it's an exception to this rule. So we're going to put PPT there, or downward facing arrow. And then nitrates, what's the rule for nitrates?
None.
So are they in the top category or bottom? Top, so they're all wet. Soluble, so what do we write here? AQ. Okay, so will this reaction occur? Why? Because it's got a precipitate. Yes, it will occur because it has a precipitate. So, chlorates and acetates are not on your list either. So this is an NLO example. Okay. Oh, is acetate on there?
Yeah.
Oh, yeah, it is. Okay, so in acetate, there's no exceptions, right? They're all wet. Aqueous, all right, all soluble, so we'll put aqueous here. Chlorates is not on your list, but I'll tell you it behaves very similarly to acetate. All of them are soluble, no exceptions. So this is also wet. So what do I write? AQ. Here's what it looks like, guys. Envision this. Here it is. Okay. Bluish colored liquid poured into a clear liquid makes a light blue liquid. What happened? Nothing. It just diluted itself in like a clear liquid. Literally, we're like liquid, liquid, boom, makes liquid, liquid. We see nothing happening. So we see no evidences of chemical changes. So what do you guys think? Say again? No reaction. This would be considered a no reaction because you're literally just adding liquids to liquids and nothing happens. So if there's no chemical evidence of change, then we would indicate that it's a no reaction. Okay, I'll do some more of these. I'm doing like just a couple of practice with you so that you get the hang of each one, and then we're going to come back together on the kind of a conclusion. This is the last one. Woo! Last style of reaction. So this is usually everybody's favorite one because we deal with combustion in a fun way in the lab with Bunsen burners and fire. And it's not too challenging. Like synthesis and decomp are definitely the more mentally challenging ones because there's a lot of options. Single replacement everybody loves because you just switch one. Double replacement, pretty easy to switch both of them. You look at the rules and apply. And then combustion is also another favorite because literally the only thing that, when it says combustion, it means that you have to have what as a reactant, not just O. If you have combustion, what must be a reactant? What must be a reactant? One more time. O2, right? So oxygen diatomic gas must be a reactant. So that's a common thing you see on both of these. So I just heard O, which you mean oxygen gas. And if you have combustion of a metal, where you have a metal reacting with oxygen, this looks eerily similar to what? What other one have we learned that looks similar to this? Binary synthesis, right? Element plus element, what's the only thing they can do? Combine, right? And if we have to combine them, we have to crisscross charges to make sure we write the correct formula. Dan, favorite metal?
Sodium.
Simply sodium. Okay, sodium and oxygen, and what's it going to make? No. Na2O. You guys are not crisscrossing charges. We're all going to go get CCC tattooed on us so we don't forget. Crisscross charges. So sodium has a 1 plus, oxygen has a 2 minus, Na2O. You have to crisscross. Balance that, guys. Put a 2 in front of the sodium and so I need a 2 in front of this. And you just drop it right here on my desk. Thank you. All right, so that's our metal oxide forming, which is just an example of synthesis, really. It's just because of that we have oxygen present, we can claim it as combustion as well. All right, so combustion of a hydrocarbon. You're going to start right here. Hydrocarbons are anything that's carbon bonded to hydrogen. Do you guys remember some of these from organic nomenclature? Okay, list out, remember the number of carbons, and then there's like anes, enes, and ines. I didn't put this on your quest because I knew you were already challenged with nomenclature, and I wanted you to have a chance at life. But now we're going back into organic, and we will not escape this because we have to use them for all combustions. Like methane, ethane, propane, butane. You're actually looking at me like I'm a crazy lady. You probably want to pull out your notes from that then. Pull out your nomenclature, a little sheet that had organic on it. It's not your polyatomic ion list. It's got organic. It looks like this. It looks like that. Find it. I'm giving you like a minute to get your lives together. It was from like last week. You could not have lost it by this point. It's not a challenge. Don't lose it. Oh, find it. Yep, it's on the same acid. It's on the same sheet as the acid sheet. Okay, if you found it or not, I am moving on. Whether you have found it, I am moving on. Okay, so combustion of a hydrocarbon always makes exactly the same two products. What are the two products? CO2 and H2O. Always, 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 always. Okay, so give me the formula for ethane. Stop looking for papers. If you're not ready, come back to me. Okay, ethane. C2, because F means two carbons. Ethane. Ane means hydrogens must be what?
C2H6.
H6, because ane means 2n plus 6. I mean, 2n plus 2. 2n plus 2. So F was 2 carbons. 2 times 2 is what?
4.
Plus 2 is, that's how we got the hydrogens. Okay, so there's ethane. We're combusting it, so I must add it to what? Oxygen, and they always make what and what?
CO2.
CO2 and water. Always. Now, we have to balance this. So every single time we do a combustion reaction, reacts with oxygen, makes the hydrocarbon will always make CO2 and water. So you will balance it in this order. Show. C, H, and then O. Balance the C's first. What do I need? 2 here because I have 2 carbons here. All right. How do I get 2 hydrogens? Because I've got the C's done.
3 from water.
So I see a 6 over here on hydrogen, so I need 3 here to give us a 3 times 2 option. And then now I need to do O's. How many O's do I have over here? 2. How many do I have over here? 7. 2 times 2, 4, plus these 3, 7. So how in the world am I going to get 7 out of 2? I can't put fractional coefficients. So here I'm going to put 3. I'm going to put 7 halves because 3.5 is 7 halves, right? I'm putting that there for now as a temporary coefficient. But here's your issue. If odd oxygens, you must double all coefficients to make it work out. So double this coefficient, and what do you get?
2.
Because it's currently a 1, right? So double it, and I'm going to get a 2. Double 7 halves, and I get what? 7, because 7.5 times 2 is, cancel the 2's out, and you get 7. Double this, and you get what? 4, and double this, you get what? 6. If you end up with odd oxygens, you will have to put a fraction there. Shame on you, we can't put fractions, so then all you have to do is what for each? Double it. Let me do another one, okay? Do butane combust? Butane. I need a formula. C for butane. H10. Okay, and you guys work it out. Alright, check yourself on the board, and you can see the thought process hopefully behind this. You probably put 4 on carbons and then 5 on water at first. Then you realize you had 13 oxygens, you're like, darn it, 13 halves is what you would want to write, but we're not allowed, so you go through and double them all. Alright, so you were like nomenclature masters at this point. If you're not accessing your poly list, you're using your periodic table, of course, but you're doing pretty good with nomenclature, I feel. Organic structures or organic ones are going to trip you up for a moment until you get the hang of that once again. But I feel pretty confident you're able to move on to homework. Okay, so I can do some more up here, but I want to see where you are. So if you want to pull out the homework from last night, which was single and double, synthesis and decomp, it's on the same sheet that you were working on last night. And there are 15 minutes. Okay, you have 15 minutes. Maybe we can knock those out? Yeah. Take the mic.
So then we don't need, is it treasure lead or is it?
Well, zinc. So Bryce, zinc is a what? So it has to switch with a. Well, no, then, but since it's like it'd be the same. So nitrate state is still. So all you're doing is switching the two metals. So then this one, cations replace cations. That's kind of your rule. Now.